Good afternoon to all students. So today in this lecture we are going to study what is region of convergence in Z transform. I hope you have studied region of convergence in the Laplace transform in your mathematics 3. If not, it is quite simple. Okay, in case of Laplace transform we require to use S-plane to plot the region of convergence. But in case of Z transform, as it is a digital domain, we need to use the Z plane in order to plot the region of convergence. Okay, so we will see what is the region of convergence. So we already know that the Z transform of a sequence x of n is given as this formula. We know, we have already studied this formula. We have related this formula with the discrete time Fourier transform. Also we have solved numericals related to this formula. Okay, so in the last lecture we have solved 7 problems without ROC. So in today's lecture we are going to solve the remaining problems, okay, with region of convergence plotting. Okay, so we will start with the region of convergence. Okay, this is called as Z plane. Okay, you have seen already. For example, in our control system practical, there is a practical called as to plot the zeros and poles of a transfer functions. Okay, so we were solving the characteristics polynomial in the denominator. We were finding out the roots. Okay, roots are nothing but zeros and poles. Zeros are in the numerator and poles are in the denominator. Okay, so we were plotting the poles. Poles were denoted by cross and zeros were denoted by diamonds. Okay, so that particular for that particular plotting of poles and zeros we were using Z plane. Okay, because it was a transfer function Laplace transform. Okay, in S domain, if there is a Z domain we have to use Z plane. There is no difference. Okay, this is imaginary part. Okay, this is real. Positive real, negative real. Positive imaginary means plus j, negative real means minus j. This is unit circle. Okay, so the region of convergence either be inside the unit circle or outside the unit circle, or maybe entire the Z plane. And this is nothing but this radius is r, which is 1. Okay, we have chosen the radius to be 1 or any other symbol depending upon the x of n. So the Fourier transform does not converge. Converge means opposite to the infinity. Okay, there are two terms, converge and diverge. Okay, converge means limited, finite, and diverge means infinite. So the Fourier transform does not converge for all the sequences. The infinite sum may not always be finite. Similarly, the Z transform also does not converges for all the values of Z. Okay, it is not necessary that Z transform will converge. Okay, the set of values of Z for which the Z transform converges. So if the Z transform converges and the set of values of Z for which it converges is called as region of convergence, ROC. Okay, short form is ROC, full form is region of convergence. Okay, so we are already studied that existence of Fourier transform. So the Fourier transform of x of n exists if this sum converges, means if this sum is finite then the Fourier transform will exist, otherwise it will not exist. Also that the Z transform of x of n is just a Fourier transform of the sequence Z transform and Fourier transform are relatable. Okay, we have seen the relation. There is only the difference, which is R. Okay, and the Z transform therefore exist or converge if this condition is satisfied. If this condition is satisfied, then we can call as then we can say our Z transform X of Z converges. The condition is nothing but the summation of the Z transform is less than infinity. Okay, means 1, less than 1. So now we can see that. Okay, so this is the shaded portion is nothing but the region of convergence. You can uh, display region of convergence in shaded portion or by introducing the bars. Okay, or uh, triangles or any other indication. Okay, so in specific cases, the inner radius, there are two types of radius. Okay, this is the inner radius and this is the outer radius. Okay, so in specific cases, the inner radius of this ring may include the origin. Okay, the Z transform, sorry, the region of convergence has origin at Z equals to 0. Okay, and the outer radius may extend to infinity. So if the ROC includes the unit circle Z, mod of Z equals to 1, then the Fourier transform will converge. Okay, so we will see this is the transfer function formula. Okay, P and Z, P and Q are polynomials in Z domain, and so the values of which Z for which P of Z equals to 0 as called as 0 of X of Z means these Q are called as poles, these are zeros. Okay, so we will take an example. So we have seen in the numericals solved earlier, there are types of numericals. Okay, first one is a right-handed sequence, second one is left-handed sequence, third one is finite sequence. Okay, fourth one is a type of weighted sequence. Okay, sum of two sequences is called as weighted sequence. So we need to see the Z transform for different sequences. Okay, so first of all, we are going to see this right-handed exponential sequence. Okay, so we have already seen this example, a to the power n u of n. Okay, I'll show you the example. This is okay, the example x of n equals to a to the power n u of n. So this PDF is different. Okay, this PDF is designed for this lecture, and in the earlier PDF there is only solution of Z transform. There is no any solution of region of convergence, and in this PDF I have solved the problem also, and after the problem there is a region of convergence. Okay, solution to the region of convergence. I have identified the region of convergence for each and every problem. Okay, you can I have uploaded this PDF into the Microsoft team. Okay, you can check it out. Also this PDF is also uploaded in the teams, you can check it out. If there is any problem, contact me. Okay, so where we were stuck to this problem. Hmm. So this problem is nothing but this is positive, this is also positive, so it's a basically right-handed sequence. Okay, this u of n is right-handed sequence, so a may be exponentially growing or decaying. Okay, depending upon the value of a. If it is less than 1, it is decaying or converging. If it is greater than 1, it is non-converging. Okay, going to infinity. So we have already seen the solution. Okay, This is the solution. So now the point at which we are going to find out the region of convergence is before the solution. Okay, it is the point at which the summation ends, before ending the summation. Okay, this is the point at which the summation ends, and this is the second last point. Okay, so we have taken the summation of this whole part, and then we have gone to a solution. Okay, so this is the point at which we are going to find out our region of convergence. So in this PDF they have taken the same sequence, alpha to the power n u of n. Okay, so this is the point at which we have to find out the region of convergence. Okay, so we know that for the Z transform to converge, this should be less than infinity. Okay, which ultimately means that this term A and Z inverse, okay, mod of this term should be less than 1. Okay, this whole term means this should be less than infinity, means should be less than 1. Okay, so which indicates that this term mod of A into Z to the power minus 1 should be less than 1. Okay, so I've solved here. So region of conversion of this. Okay, so this is the right-handed sequence already, we know that. So therefore for right-handed sequences the region of conversion is outside the outermost pole. Okay, so how to find out the pole? So what we will do, we will take this numerical, okay, in deep. Before that we are going to see how region of convergence is find. Okay, found. We already know that if this is less than 1, then the Z transform converge, it will become finite, or this is also equivalent to Z greater than A, because here I have solved. So this is the condition, okay, less than 1. So when we simplify Z inverse, it will become 1 upon Z. Okay, so alpha upon Z mod of is less than 1. So when we will cross multiply Z with 1, it will become positive Z. Okay, so mod of Z is greater than alpha. That's it. Okay, mod of Z is greater than alpha or A. So how to use this? Okay, so it's a right-handed sequence, and the region of conversion is outside the pole. So here alpha is the pole. Okay, if the alpha is not given, any other variable is not given, pole is by default 1. So in this case alpha is given, so the pole is A. So RO region of convergence ROC is outside the pole. Okay, you can see here this is Z plane. We have to indicate the region of convergence. Okay, so as the fundamental rule says that for a forget the fundamental rule, what they have given Z should be greater than alpha. Okay, so we have to plot alpha anywhere, okay, in the positive real axis. This is where I've plotted the alpha here. Okay, and what okay, this is nothing but the Z. Okay, this much means radius is r equals to 1. This is Z. Okay, so for a right-handed sequence the region of conversion is outside the pole. So inside the pole we cannot draw or we cannot indicate the region of convergence. We have to indicate region of convergence outside the pole A. Okay, so they have shown here by, okay, You can see here, this inner part is white and the outer part is quite gray. So this gray is nothing but the region of convergence. So for this region of convergence outside the pole, our Z transform converges. Okay, so why we have chosen outside the pole? Because Z is greater than A. Okay, A is nothing but the pole. Okay, this is example for right-handed sequence. So if we have given example like a left-hand sequence, okay, which includes minus in u of n. Okay, so what will happen? We have also solved this problem here. Okay, this is the problem we have solved already. This is the left-hand sequence because u consists of negative terms and a delay time shift. So it is a left-hand sequence. Now this is the point at which we are going to find out the ROC. Okay, because after this point the summation ends and we have mm, got a solution. Okay, so the point which is before the solution, which consists of some summation, is the point of ROC. Okay, so you can see here they have solved the example, and this is what I was saying. Okay, this is the condition for ROC. This is the point at which we are going to find out ROC. Okay, now what is necessary for that? This should be less than 1. Okay, so they have given mod of a to the power minus 1 z less than 1 or z less than a. So I have simplified it. This is a left-handed sequence. So as in the right-handed sequence, ROC is outside the pole. So in the left-handed sequence, we have to do opposite. ROC is inside the pole alpha. Okay. The condition for ROC, sorry, the point for ROC is this. This should be less than 1. Okay. Here I have drawn. Okay. So now after simplifying alpha inverse, it will become 1 upon alpha. So this will become z upon alpha less than 1. So when we cross multiply alpha with 1, this will become mod of z less than alpha. So whenever your z is less than alpha, the region of conversion is inside the pole. Okay, so we on this previous problem we have seen alpha is the pole. Okay, so alpha drawn here. Okay, I will show you this in this example. So alpha is drawn over here. Okay, and is as z is less than alpha, so the region of convergence is inside the pole. So you can see that outside the pole there is a white region, which means that there is no region of convergence outside the pole, but inside the pole the region is indicated by gray color. Okay, so this is nothing but your region of convergence inside the pole. Okay, inside the outermost pole, this is the outermost pole. Okay, this is for left-handed sequence. So if there are two exponentials, for example, in this we have taken the example. Okay, so there are two sequences. So in this case, what to do? How to draw the region of convergence? Okay, so in this case, we have to use the intersection property. Okay, property or topic or concept. So they have given the example and they have solved the example. Okay, so this is the condition. So we have already solved this example. It is very simple example. So this is the condition or the point from which we are going to find out the region of convergence. Okay, because after this point we have got a solution. So the point which is before the solution is called as the point of region of convergence. Okay, so now this and this should be less than 1. Okay, so mod of this term and mod of this term should be less than 1 in order to converge. So I have shown here, you can see clearly. So mod of this should be less than 1. Okay, so 1 upon 3 into z inverse less than 1. So take 1 upon 3 outside of the mod, then simplify this will become 1 upon z. So 1 upon 3 into mod of 1 upon z less than 1. So when we cross multiply this 1 upon 3, or this z goes here, so it will become mod of z greater than 1 upon 3. Okay, so z is greater than 1 upon 3. This 1 upon 3 is nothing but your pole. Okay, outermost pole, one pole. Okay, so for the second point, you can see here clearly, this is the second point. So mod of this term, so mod of 1 upon 2 into z inverse should be less than 1 to converge. Okay, so when we simplify, z inverse will become 1 upon z. Okay, take 1 upon 2 outside, cross multiply z with 1, so it will become mod of z greater than 1 upon 2. So the first ROC is mod of z greater than 1 upon 3. Second ROC is mod of z greater than 1 upon 2. So we need to take the intersection. Okay, intersection means nothing but we have to choose the greater one. Okay, so between from this and this terms we have to choose greater one. So this is nothing but 0.33, this is nothing but 0.5. So between these two, zero point 0.5 is greater. Okay, so whenever we take any intersection we choose the greater point. Okay, so I've written here ROC is this intersection of this. Okay, so choose. So now intersection of R1 and R2 means this is R1, this is R2. Okay, intersection of R1 and R2 is the greater one. Okay, so this is 0.33, I've already said. This is 0.5. So now z greater than 0.5 is greater term. Okay, so we have to take only this one because it is greater than this term. That's what intersection happens. So this 1 upon 2 is our outermost pole, 1 upon 2 or zero point 0.5 on the real axis. So this is our outermost pole. In this PDF they have given this is half outermost pole. Okay, and this is the second pole. So we have to choose the greater one, and as this sequence is a right-handed sequence because there is no negative terms in u of n, so the ROC will be outside the pole. Okay, so it will be outside the pole 1 upon 2. So inside the pole there is no ROC present because it is a right-handed sequence. The ROC will present outside the pole. So they have indicated by gray marks. So I've indicated by this kind of lines. Okay, inclined lines. Okay, you can indicate this also because this is quite difficult to draw. Okay, to it's quite painting. This is quite simple. So ROC is outside the pole half. Okay, so this is about the example of two signals. Okay, So now if there is a finite sequence, finite length sequence, okay, for example, hmm, this is a finite sequence, okay, because it has already I've shown you this is only present for x of n equals to 0, otherwise it is 0, so it is a finite sequence. So for this, the z transform, sorry, the ROC is entire z plane. No need to draw, no need to find out any poles. ROC is entire z plane, so you can show like this, okay, all over the plane. So in conclusion, you can say that for left-handed sequence, ROC is inside the pole or unit circle. For right-handed sequence, ROC is, for left-handed sequence, ROC is, sorry, I'm just got confused. For left-handed sequence, ROC is inside the pole or unit circle. For right-handed sequence, ROC is outside the pole or unit circle. Okay, and for sum of two signals, ROC is the intersection of two poles. Okay, so which one is greater? We have to choose, and depending upon the sequence of signal, you have to indicate their ROC. And for finite sequences, ROC is the entire Z plane. Okay, so now properties of region of convergence. So these properties depend upon the nature of signal: exponential nature, right-handed sequence, left-hand sequence, finite sequence, okay, weighted sequence. So first property is the ROC is a ring or disk in the Z plane. ROC is nothing but a ring or disk in the Z plane, okay, with radius 1, centered at the origin. Okay, this is a basic point. Second is the Fourier transform of x of n converges absolutely if and only if the ROC of the Z transform include the unit circle. Okay, so the Fourier transform converges only when the ROC of our Z transform includes unit circle. Means ROC, this is ROC. Okay, this is including the unit circle. If it is not including unit circle, then Fourier transform will be non-converging or diverging. The ROC cannot contain any poles. Okay, you can see here in this example, ROC is outside the pole. Okay, in this example, ROC is inside the pole. So ROC is not containing any pole. Region of convergence does not go through the pole. So if x of next property is, if x of n is finite duration, that is 0 except on finite interval, the ROC is the entire Z plane except perhaps at z equals to 0 or infinity. So this is an example. This is this example satisfies the property. We will see after this property. Okay. So if x of n is a right-handed sequence, then the ROC extend towards from the outermost finite pole to infinity. Already we have seen if our sequence is a right-handed sequence, then the ROC is outwarding from the pole to infinity. If it is a next property is, if x of n is a left-handed sequence, then ROC extends inward from the innermost pole to z equals to 0. So we have already seen, if our sequence is a left-handed sequence, negative sequence, then ROC is inside the inside the pole to z equals to 0. So next property is a two-sided sequence, neither left nor right-sided, has a ROC consisting of a ring in the z plane, bounded on the interior and exterior by a pole, and not containing any pole. Okay, this is the same two poles. Okay, bounded, and the ROC consists of this. Okay, this we have already seen the example. And last property is the ROC is a connected region. Okay, so these properties are important for the exam. Okay, and now we will see the examples. We've already seen the examples. Now we are going to find out the ROC. So already in the first example we have seen x of n equals to u of n. This is a right-handed sequence. Okay, so the property states that the ROC will be outside the unit circle or pole. So there is no pole here, only u of n is present, and this is the point at which we have to find out the ROC. Okay, I have given here in the notes, you can see this is importance for convergence. Okay, so this z inverse should be less than 1. This is the point at which you have to find out your ROC. So to converge, the value of z inverse should be less than 1. Okay, so the region of convergence is given. So I have given two examples. For example, summation of n equals to 0 to infinity. Okay, half to the power n. So in we have already seen that this sequence will be decaying. Okay, this is a decaying sequence. So first value is higher, second value is less, half half, it will become to 0. Okay, so it is a finite sequence. So this one converges to finite value, which is 2. So this 2 is nothing but 1 upon 1 minus half. So this summation converges to finite. Okay, decreasing. So again, second one, if this is greater than 1. Why I'm showing you these examples? Because this is less than 1. Okay, our condition is what? This should be less than 1. So if it is less than 1, then the Z transform converges to finite value. If it is greater than 1, then here is 2, it will be infinity, because the sequence will exponentially grow. This will be infinity. This summation diverges. Okay, it will not converge to infinite. Okay, so if the value is less than 1, the summation diverges. If this value is greater than 1, then the summation diverges. Diverges is opposite of converges, otherwise converges. Okay, so condition is given as this should be less than 1. Mod of z of mod of z inverse should be less than 1. So after simplifying this will become 1 upon z. So mod of 1 upon z should be less than 1. So after then cross multiplying it will become mod of z greater than 1. So it is right-handed sequence. Okay, and z is also greater than 1. So this is your region of convergence plot or z plane. Okay, this is imaginary, which is plus j, here is minus j, plus real, minus real. Okay, this is one unit circle. Okay, in this problem there are no poles, so take unit circle 1, r equals to 1. Okay, if there is no pole, take r equals to 1. Then we can see that z is greater than 1. So our region of conversion is outside the unit circle. Okay, I have shown by the red lines. Okay, inside the unit circle there is no region of convergence, it is blank. Outside the unit circle there is region of convergence indicated by the red lines. So if the value of z is greater than 1, then x of z will not have finite value, and vice versa. If it is less than 1, it will have finite value. So area of z outside z equals to 1 is the ROC of u of n. Okay, so area greater than this one is ROC of this sequence u of n. Okay, you can understand. Okay, simple problem. So next problem you are already seen. This problem is left-handed sequence problem. Okay, so it is vice versa or opposite to the right-handed sequence. So in left-handed sequence problem, the region of conversion is inside the unit circle or pole. So here in this problem there is no pole, and we have already solved this problem in the last lecture. So this is the point. This is the point at which we have to find out ROC. Okay, this is the moment we are going to find out ROC. So now how to find out ROC? Simple, eh? As it is a left-handed sequence, you can see here this is only z. Okay, not z inverse. So z mod of z less than 1, no need to simplify, it is less than 1. So if it is less than 1, the region of conversion is inside the unit circle or pole. So if there is no pole, take radius 1, so it is inside the unit circle. So this is left hand sequence, and the region of conversion is inside the unit circle. Okay, so next problem is a finite one. We have seen a right handed sequence, then left handed sequence, and third one is a finite sequence. Okay, so this finite sequence is available only for n equals to 0. Okay, if we have solution, answer is 1. Okay, so now for a finite sequence, the the region of conversion is entire z plane. Okay, so to find out the region of conversion of del of n, this del of n, so it is a finite sequence. So ROC, as I already said in the properties of z transform of ROC is entire z plane. Okay, so I've shown the ROC by these red lines. Okay, this is the ROC, entire z plane. So now next problem. So I was talking about this property, this one. There are two finite sequences. Okay, a simple finite sequence and with delay. Okay, this is the property. This property is for this problem because in this problem del is with a time shift of minus k. So del function will available only for k. Okay, so now to find out the region of convergence of this, it is also entire z plane. Okay, there is a small difference. This is also a finite sequence, so ROC is entire z plane. Expect z equals to 0 when k is greater than 0. Okay, so for this z equals to 0, the ROC is not present, and for infinite value when k is less than 0, ROC is not present. Okay, but the ROC is entire z plane. Okay, So it will be absent at the point 0 and infinity. So in between it is present. So next we have to see this we have solved already. It is a right-handed sequence with a pole. Okay. So this is the answer for that problem, and this is the point at which we have to find out the region of convergence. So condition क्या है? Alpha z inverse should be less than 1. Mod of this term should be less than 1. So I have shown here. This is a right-handed sequence. Therefore, ROC is outside the outermost pole. Here we cannot take the unit circle because there is a presence of pole. So ROC is outside the outermost pole. So this is the point. So after taking mod of this term less than 1, we can simplify. So by simplifying, z inverse becomes 1 upon z. So mod of alpha upon z less than 1. So after cross multiplying z with 1, this will become mod of z less greater than alpha. So alpha this z is greater than alpha, and this alpha is a pole because we can see that this term, or for example this term. So whenever we are going to find out the poles, we need to see in the denominator. Okay, this is a pole, this is a term. Okay, sorry, this term when equals to 0 to find out the pole. Okay, so put equals to 0, then what will become? This will remain as it is. This will become -1, this will be -1, minus minus gets cancelled. So z will become alpha. Okay, the radius will be alpha or a pole. So alpha is a pole or radius. So as z is greater than alpha, the ROC is outside the pole. Okay, this is the pole alpha drawn here, and the ROC is outside the pole. Inside the pole there is no ROC. Outside the pole there is ROC. Okay, up to infinity. Okay, so next problem. This is a negative sequence or left-handed sequence with a pole. Okay, I've also shown you this problem in this PDF. If you remember, this is a negative or left-hand sequence. Okay, we have solved this already. This is the point at which we have to find out the region of convergence. Okay, so I have shown here simplified. So the ROC of the sequence is, first of all, it is a left-handed sequence. Therefore, the ROC is inside the pole. So as there is a pole, we have to say it is inside the pole. If there is no pole, we have said it is inside the unit circle. So this is the condition. This is the point from which we have to find out the ROC. So now what we have done, take the mod of this here less than 1. This is the condition. Okay, after so simplify it. So alpha inverse will become 1 upon alpha. This will be z upon alpha, mod of z upon alpha less than 1. So after cross multiplying alpha with 1, it will become mod of z less than alpha. This is our ROC. Okay, so as it is less than alpha, it is inside the alpha. Okay, ROC. So I have drawn here alpha is our pole, outermost pole. So it is less than, z is less than alpha. Okay, so ROC will present inside the outermost pole alpha. Okay, simple problem. So now next problem and last problem is our weighted sequence. Okay, two signals. So we have already solved this problem in the next lecture. You can refer the video, lecture number 8. Okay, this is the point at which we have to find out the region of convergence. So I'll zoom it. So this is a weighted sum of two sequences. Okay, why it is called weighted sum? Because this is a u of n minus b u of n. A and b are the weighted sums. Okay, so the ROC is the intersection of the signals. So we have to find out the ROC for this first, then ROC for this, then we have to intersect the ROC by choosing the greater value. Okay, so now this is the condition I've already said to you. Okay, for the ROC, finding out ROC. So now we have to take the mod of this less than 1. So we will denote this term as R1, this term as R2. R1 means ROC of 1, R2 means ROC of 2. Okay, so mod of this is less than 1. Okay, here. So now take 1 upon 3 outside. Z inverse will become mod of 1 upon Z less than 1. So after cross multiplying Z with 1, we will find out mod of Z is greater than 1 upon 3. It is coming greater because it is a right-handed sequence. Okay, this sequence is right-handed sequence. Both the sequence are right-handed. Second one, R2. Okay, mod of this term less than 1. Okay, take 1 upon 2 outside. Z inverse will become 1 upon Z less than 1. So cross multiply Z with 1. Okay, so Z mod of Z is greater than 1 upon 2. In both the ROCs, Z is greater. Okay, so now we have to find out the intersection. Intersection is nothing but we have to choose the greater value. So this is 0.33, this is 0.5. So among both, this one is greater, 0.5. So I have shown here. Now the intersection of R1 and R2 is the greater one. Okay, that is Z is, first one is Z greater than 0.33, second one is mod of Z greater than 0.5. So mod of Z greater than 0.5 is greater. Okay, so take only mod of Z greater than 0.5. So 0.5 or 1 upon 2 is our outermost pole. So whenever there is intersection, we have to choose the greater ROC, and then we have to denote that term as our pole. So I have chosen here 1 upon 2 is our pole. Okay, outermost pole, and this is a right-handed sequence. So ROC is outside the pole. Okay, pole is 1 upon 2, ROC is outside the pole to infinity. So inside the pole there is no region of convergence because this is a right-handed sequence. Okay, so this is for today, and I will be uploading this lecture on YouTube. And if you have any problems regarding the region of convergence concept or the properties, feel free to ask. And everybody are requested to watch the video. Okay, the number of count on video is quite less. Strength is 80, but count is only 30, less than 30. So all need to watch the video, and the final exam will be dependent on the videos and the PDFs. Okay, so refer both video and PDF, and while watching the video, refer the PDF so that it will give you a better understanding and a clear vision regarding the concepts. Okay, so in the next chapter, so in the next lecture, we will see the properties of Z transform and inverse Z transform. Okay, so Goodbye and have a nice day and stay safe, stay home and take care all.